So today we're going to talk about linked lists, and you guys should be in the middle of implementing a linked list. We didn't talk about it to any great extent, but we will today, and introduce the idea of big O notation, and in the context of a linked list and array list, kind of understand how and why we might want to choose one implementation of an abstract data type over another, right? Okay, so a linked list implementation of a list is exactly the same interface that we implemented when we did it with an array. It's just a slightly, a different strategy in terms of how exactly it works, right? So if I have a linked list and I have an array list, they both are implementations of the interface list. And wherever I need a list, I can use one or the other. And it will not matter functionally from a what it can do point of view which one I use, right? So, that begs the question as to why we have a difference, right? And that's what we're going to talk about a little bit today, after we go over the details of how a linked list works, right? So we know how an array-based implementation works. That's the one we actually did in class. We use an internal array to store our elements. We keep track of the size of the list, and we use the first size elements of our array in order to store it. And then we make that array bigger. We make it bigger than we need at first, but then as we add things to the list and we run out of storage, we double the size of the array and copy it and replace our internal storage. So the person using our list doesn't have to know any of this is going on. They just use the list. And inside, as we add things to the list, our array gets bigger as necessary, right? A linked list implementation takes a different strategy. Instead of having an array of elements where, as its storage, it uses a chain of nodes, where nodes basically are simple data structures which combine a value, right, a particular element value, and a pointer, a reference to the next node in the chain. And the idea here is a linked list implementation of list also keeps track of size, just like our other one did. But this time, instead of storing its elements in an array, it keeps track of the head of this chain. And whenever we want to do anything with the list, add something, insert something, retrieve something, etc., we essentially walk down the chain until we find the place that we need to do something, and then do it and make adjustments as necessary, right? So the last slide that we saw in the previous lecture was this one. It was very quickly at the very end, kind of demonstrating the difference between an array list and a linked list as they are represented in memory, right? And so on the top, we have that first box to the left, which has got the memory address 0x3425. That might be an array list, right? That might be our array list structure. And our array list has, right, internal fields. The fields of an array list include a size and a reference to the array, which I'm showing here as a pointer to this other structure in the heap, which is our array, right? Now notice the size of the list is 3. The size of the array is 10, right? The idea being that the array needs to be as big as the list for sure, but is usually often bigger than the list needs in order to have room for adding things. And we can see that being demonstrated by the fact that everything past index 2 is set to null, right? So here's an array of strings that is our storage for our list of strings, right? And elements is as the field inside our array list points to this array. That's where our storage is. That's where it's actually being stored. And then the first 3 things are references to the first 3 strings. And the rest is null at first, right? And then if I add something in the fourth, if I add something to the list, the size of the list goes up, and I use the next empty spot in the array to store that next thing in the list. And I keep adding things to the list. The size of the list keeps getting up. And then we saw when we were implementing this, when the size of the list equals the size of the array, we'll have to create a whole new array that's bigger than our original array, copy everything over, and then update our elements to a field to point to this new array. Basically, we'll make the storage bigger. And then, of course, each of the individual strings is an object on the heap, and they're referred to through the pointers where they're in the elements of the array, right? So that's our array list implementation. A linked list implementation is going to look like something that, like below. Like array list, it will also have to keep track of its own size, right? And make sure that it's consistent and adjust it as we add and remove things. But instead of a pointer to an array where the elements live, it's going to have a pointer to the head of its chain of nodes. And so a node is a small little data structure that looks like this, which has each node has a value, right? In this case, it's each of these are nodes of strings. So each one has a value, which is the specific string being stored at that node. And it has a field which keeps track of the next node, the next node in the chain. And so by holding on to the head of the chain, the head then points to the next one, which points to the next one. And we know we're at the end when next is null. So the fact that the next value for the last node is null is essentially the indicator, we're at the end of the chain, right? And so, so here are two lists that are storing the same 3 elements, but in very different ways. One as an array list, and one as a linked list. Right? So going through the details of how a linked list works without actually writing the code, because you guys are going to write the code, what does it mean to be an empty linked list when we start off with if I say new linked list and therefore it's empty? Well, it's pretty clear, right? An empty linked list would have its size be 0 and the head be null. There is no node, right? There is no chain, right? It's null is the end of the chain, head is the end of the chain. That's because there's nothing in there. And size is 0. Okay? So that's fairly straightforward, hopefully. Now let's think about what happens when we want to do something like get a particular index, right? So remember, that's one of the operations that a list needs to be able to do. When we have a linked list, then the idea here is that first, right, the algorithm for get an index, the index or the IDX index of a linked list is first confirm that IDX is valid. We should be able to do that with the value of size, right? Because if we're going to get a particular index, it has to be between 0 and size minus 1. So that's easy enough to do. And then what we basically do is we start at the head of the list and keep track of a counter. And we walk the chain until the counter is the same as the index we're looking for. And then we know that we're at the right node, right? So let's see what that looks like graphically, right? So let's say we're trying to get the index 2 of this list in structure, this array, this linked list, which I'm kind of showing you what it looks like in memory, right? So this very first box here with the X5A32 address, that's our linked list, right? And I'm asking that linked list, please get your index 2, right? Step 1 is to check to make sure the value 2 is a valid index and throw an exception if not, right? So is 2 between 0 and size minus 1? Yeah, it's good. So that works. So we know that this item exists. If it didn't, right? If the index was too big or the index was something nonsensical like -1, we should throw an exception, right? Now in this case, and this has come up on Piazza, I've generally told you that whenever your program needs to indicate something's wrong, that you can always throw a runtime exception by saying throw new runtime exception and then provide some sort of explanatory message, right, to the constructor of the runtime exception, as the parameter to the runtime exception constructor, right, and that's how you do it. That is true. That is still how you do it. Now, it turns out that what I didn't mention is that runtime exception is not the only way to throw an exception in Java. Runtime exception is one particular exception object or type of exception object that you can throw in order to indicate a general error at in the running of your program. However, Java provides a number of what's known as subclasses of runtime exception. These are object types, right, that are still exceptions, and they are in fact runtime exceptions, but they're a little bit more specific to specific situations. And there happens to be built into the Java language a index out of bounds exception, which is particularly apropos to this problem of checking to make sure that the index is in bounds, right? And so the LA who wrote the tests for assignment 4 basically tested to see whether or not you are actually throwing an index out of bounds exception when the index is out of bounds. And so I hadn't explained that there were more than one exception typing class, and so there were some questions on Piazza because somebody had written their answer throwing a regular runtime exception, and the test came back and said, you threw a general exception. I was expecting an index out of bounds exception or no exception at all, so something's wrong. So that's why. So I posted about this on Sakai as well, but basically in your solutions for A4, whenever you are checking an index to see if it's legal and it's not legal, just throw a index out of bounds exception, because that exception is around, more accurately describes the situation than the generic runtime exception. Okay, so step 1, we check to make sure the value 2 is a valid index, and we throw an exception otherwise, right? Step 2, right, remember, is to set up some local variables for the current node, right, as we're walking, right? We're basically going to walk the chain, so we need to know where the current node is, and the index of the current node, right? So let's put our thinking caps on here, right? If the code, in order to set up a new local variable that will, a new local variable in order to, and presumably this is like the code inside of get, a new local variable to start walking the chain, and an index counter for the beginning of the chain. What are the appropriate values for current and index counter, right? So I'm going to give you a second to think about it. Feel free to talk to your neighbor, and then we'll come back and see if we have any reasonable answers. All right, so we're in get, right? So this is the code that we're writing as part of implementing the get method within a linked list. We've already checked the index. We know the index is going to be valid. I'm trying to set up these 2 local variables so that we can start walking the chain. Who has an idea for what these question marks should be? Anybody want to share? Yes? Yes, exactly, right? We're trying to start to walk the chain. So what's the beginning of the chain? It's the head. It's the head of the chain. So we start at the head, and the index associated with the head is going to be 0. And so, right? The current node, we start off by setting up the current node to be our head node and the index counter to be 0, right? And so now we want to walk the chain. What does that mean? Until we get to index counter and increment index counter as we walk, until the value of index counter equals the value of the index that we're looking for. Remember, in this example, we're looking for 2, right? So we start off in this situation, right? And we have index counter equal to 0, and the current node pointing to the head, right? I'm not gonna. I got tired of typing fake addresses and making sure they matched everywhere, so then I just started using arrows, right? So this arrow from current to the head node means, we set, right? That's the result of. Oops. That's the result of, right, having set current equal to underscore head. What's underscore head? Underscore head is a pointer to the node structure at hex AB2F. So when we say current equals underscore head, that means current is, right, a pointer to the node structure at hex AB2F, right? Fine. So this is what we're starting on, right? And we're going to walk the chain to an increment counter as we go until we're at the index value we want. We know that index counter is 0, so that's not it, right? Presumably we're going to have some sort of while loop, and we're going to walk until index counter is 2, right? Is equal to the index we're looking for, in this case 2. So updating index counter, that's easy, right? As we go from one node to the next, we'll just go from 0 to 1. So I know how to update index counter. That just adds 1 to index counter. How do I update current? How do I make current, like walk current to the next node in the chain? What does that statement look like? Right? So I'm going to give you a second to think about what that statement looks like, and we'll feel free to confer, and then we'll see if anyone has a line of code that will help me to update current so it walks to the next node. Now remember, node itself, right, as a structure has an interface. Like it's an interface, right? So in the assignment, I provide you with a node interface and a node impl a class that implements that interface. So there are methods associated with node that might help you do this. Yes?
So on the last slide,
yeah.
where you assign like node, or you assign currents to underscore head.
Yep.
How did you know what the value of underscore head was?
That's an instance field in the linked list. Presumably this code is part of the implementation of get, right? In other words, this code is inside the linked list as linked list implementation of get, right? And so linked list has access to its own instance fields, and underscore head is one of its instance fields.
Wait, so you initialize underscore head by doing like the new
Yeah, so when I create a new linked list, right, I ended up with the structure with size as 0 and head as null, right? We'll see what add looks like. And presumably I added some stuff, right? And so don't worry about how I got this structure. So somehow my linked list looks like this in memory, right? Like it's the result of adding 3 things. And it will end up looking like this, right? I'm just worried about, now that I have it like this, how do I get to the second index, right? So current equals underscore head, that's right? So that helps me, that starts me off at head, right? And index counter equals 0. So these are presumably local variables inside the implementation of get, right? And now what's the next line that I need in order to, while my index counter is not yet indexed, I'm not showing you that code. I'm not going to actually do the homework here, right? So you still have to do the homework, right? I'm showing you little snippets of the homework, if you will. Now, what is that statement inside that while loop while you're waiting for index counter to be the same as index, right? Anybody have an idea? Yes?
Why the next is not null?
What? Why is next not null?
Yes.
Which next?
Next null.
Hmm?
Next null.
The next node?
Yes. Why the next node is not null? We can go through the.
Oh, while the next node is not null. Okay, so actually that's not quite how that while loop is going to work, because we're gonna say while my index counter is not equal to the index I'm looking for, right? In this case, 2. Okay? So the while loop is actually going to compare index counter to the index that I'm looking for. Inside my while loop, while the index counter is not equal to index, inside there I have to increment index counter. So that I know how to do. That's just adding 1 to index counter. But I also have to update the current pointer to the node, and that is the code that I'm looking for. What line inside that while loop will help me update my current value to be the next node in the chain? Close, right? Yeah.
Current is assigned the value of head, not get next.
Okay, so sure, in this particular case where current and head are the same, then we could say current equals heads, which is pointing to that same node, get next, right? Because remember, node has a get value and a set value and a get next and a set next. So assume that node, as its little structure, these little node structures, have a way to get and set their value and that next. So that would work just this one time if I say underscore head, but then I'm stuck, right? So what does it should be?
Current equals current dot get next.
There you go, right? So I set current up to be the beginning of the chain, and now once I'm at the beginning of the chain, that's fine. I don't need head anymore. Now I can just keep using current and update current. So exactly right. So what I want to do is I want to so in order to update current so that it's the next node, I can say current equals current get next. So current points to this node here. It has a get next method as a getter for its next field. So I can just I can use the get next method of the current node in order to get the next node, and then reassign current to be that next node, right? And now, after I've done that, and then I increment my index counter, I'll end up in this situation, right? So now I add 1 to my index counter, so now it's 1. I say current equals current.getNext in order to move which node my current variable is pointing to from the current node to the next node, and now make that the current node. So now it points there. And I'm still in my while loop, while index counter is not equal to the index I'm looking for. So 1 does not equal 2. I guess I need to do this again. So I keep walking. I walk until I get to this situation where, I finally have walked the chain to the point where index counter is the same as the index I'm looking for, right? And at that point, I can do the last step, which is, return the value of the current node, right? Because now I've walked it to the correct place. Now I know, okay, so here's the node that is the one I'm trying. Please retrieve the value, the element in that node, and return it, because that is what I'm trying to do. I'm trying to get the index 2 element of this list. So that's what I mean by walking the list. Right? So did anyone, any additional questions about how we were able to implement get? Right? First, we accepted as a parameter to get an index to get. We can check that index for being valid by doing the appropriate checks against size. Right? Can't be negative, can't be greater than size minus 1. And then we can start at the head and in a while loop, right, keeping track of an index counter and the current node, walk the list, incrementing the index counter and updating the node pointer until we find the appropriate index counter, the node at the appropriate index counter, and inside that node, there's the value I'm looking for. Yeah.
If you return, like say you write return current, would that return the value of the node?
No, it wouldn't. Current, the type of current is a node. So it's going to return a node. And so, that would not be returning a string. That would be returning a node. So that would be not be correct, right? You need to return the thing that's at the node, stored at the node, right? All right. Any other questions about how we implemented the algorithm for getting a particular index value from a linked list? All right. Okay. Let's try adding. Okay. So what is the algorithm for adding an element to a particular index? To a linked list at a particular index. Right. Step 1 is pretty much the same. Confirm that the index value you're trying to add this element at is correct or is valid. Now, adding at a particular index number is slightly different in terms of which index numbers are valid. When I retrieve or when I remove something, then I can only use the index values from 0 to size minus 1 because those are the valid index values for retrieving or removing a particular element at a particular index value. When I'm adding a value to the list at a particular index value, certainly I can add at the beginning at index 0, but I can add all the way up to and including size, because adding at size is the same thing as adding at the very end, right? While the valid index values for getting and removing are 0 to size minus 1, the valid index values for adding go from 0 to size. But in any case, right, step 1 is confirming that the index that I'm trying to add at is valid. And then it's very similar to getting, except that we have to stop slightly sooner, right? Because we don't want to walk all the way to index. We actually want to walk all the way to index minus 1. And the reason why is because we need to insert our new node after index minus 1. So if we walk all the way to index, the problem is we'll walk too far. We need to walk up to, but not quite at index. So we're going to walk all the way into index minus 1. Then we need to create a new node structure to insert into our list, right? And so that's basically like in the assignment, I provide you with NodeImpl, which is an implementation of Node, and again parameterized by the type T, whatever that is, right? And that is a very simple structure that is simply two fields: a value of type T, whatever that is, and a pointer to the next node. And it has a simple it's just get and set. You can either get and set either one of those fields, and that's it, right? So the node is a very, very simple structure, right? So, but the point is that I have to create a new node, and in order to create a new node, I have to provide a value and a pointer to whatever I want to be the next node of this new node, and so I need to create that. And what I want to do is I need to create that node to be, the value is the element I'm trying to add. That makes sense. And the next node for that new node that I'm trying to insert is going to be wherever the index minus 1 node points to. In other words, I'm walking to the point where I got to index minus 1. I know that the node at index minus 1, right, that point in the chain, points to the node that is at index, right? IDX. And so what I'm trying to do is I'm trying to put a new node between this node and that next node. So what I can do is I can walk to that point, create a new node so that it points to my current next, that next node, to index minus 1, and then I can update the node at index minus 1 to now point to my new node. Right now, its next value is pointing to the node at index. No, it could be. It's whatever. I mean, if it happens to be at the end of the chain, it will be null. If it's the 4th thing, it'll point to the 5th thing. It's the 12th thing, it'll point to the 13th thing. If it's the 2nd thing, it points to the 3rd thing. It's whatever is the next thing, right? Well, yeah. Okay. So I think you'll see it a little bit easier if we actually illustrate it, right? So we start off, right, to add, let's say, a new item. So we're assuming our nodes are nodes of strings here. So if we're adding a new string at index value 2, the first thing we do is confirm that index is valid, and it is. So, the size of the list is 3. I can add at 0, 1, 2, or 3, right? So adding 3 is adding at the end. Adding at 2 is basically trying to put it between another string and something else, right? That's a string, that's index 0. Another string, that's index 1. Something else, that's index 2. if I'm adding inserted item at 2, that means I'm trying to put it at 2, which means I want something else to now be 3, this new node to be 2, right? And, and to put it in between another string and something else, okay? So we confirm IDX is valid. Now we walk the chain until we find node index -1. What's index? Index is 2. So we walk until we find the node at index 1. We know how to walk, right? We have a little while loop. While my index counter is not equal to the counter that I'm looking for, or the index that the index value I'm looking for, update index counter and update current. We already know how to update current, right? So we'll walk once, and now we're here, and now we're here. We got it, okay? This is it. This is the index -1, right? I'm trying to add it 2, so I need to walk until I got to index 1. And now I'm here. I'm at index 1, right? So the next step in the algorithm is create a new node, right? So we're going to have something like this. This happens to be a node of strings. A node of a linked list of strings, and so I'm actually putting the type there, right? Now you're going to write it generically, so it'll all just be node of t, list of t, and you just use t wherever you need the type of the thing. But here, this is it. This is where I need to create a new node, right? So presumably, I'm going to have some line of code that says new node equals, and now what is that? No.
Why would you do node impl there?
Oh, it will be node impl. I'm sorry. Yes. So I need a new object that implements node. You're right. Absolutely correct. I'm so sorry. We need a node impl, right? Now, that means that's the new node impl is what the object we're creating. The type of this new node is node because we program to the interface, right? What do we need this for? We need it for being a node, right? So when we say new, we have to provide a concrete class that implements something. But then when we refer to it, we always use the interface as the type because we want to program to the interface, not the specific implementation, right? All right, so I'm going to give you a minute to think about what this line should look like, right? So here's our situation. We've walked it to this point. We know that we're going to create a new node that is going to be between our current node and the one after it, but I need to create that structure. So think about what that line looks like, and I'll come back to you in a minute. Feel free to share with your neighbor. All right, anybody care to share? How about up in the back? Come on. One of you. I won't force you, but soon enough. Who thinks they know what the rest of that line of code looks like? Yep.
New node impl.
Good.
And then element current dot get next.
Good, exactly right, right? We're trying to create a new node structure, so that's a node impl, right? So it's a new node impl of, in this case, string, but again, you'll write it generically, right? And then that constructor, the node impl constructor, takes 2 arguments. The first argument is the value that's being stored at the null at that node, right? In this case, it is our inserted item string, right? So inserted item. And the second thing is going to be a pointer to what you want that new node to point to as its next node. So when I do this line, right, it's going to create, right, a new node, right? That's going to be my local variable that points to a structure. That's the object that I just created, the node impl, and it'll have, and in constructing it, I gave it a value of that string, inserted item, and I told it that next needs to point to currents next. So right now, my list is a little bit in flux, right? I've created the new chain, link in the chain, and I've connected it to the thing that it needs to connect to. So that's good, right? But now I have to fix things up. I need to finish the step 3, which is to repoint. In other words, update the node at index -1, which in our picture here is what current is pointing to, in order to have it, instead of pointing to what it used to point to point to the new node, right? I want to update it so that instead of pointing to something else, this node here points to my inserted item in order to fix up my chain, right, and complete the insertion. So what is the line of code? What's the statement that will accomplish going from this to this? Basically, updating the node at hex 2F43 instead of pointing to the node at hex BAC3 to make it point to the node at hex 1FAC, right? How do I get that arrow to move? Oops. All right. Any ideas of what that statement is? Yeah.
Would it be current.setNext new node?
Yes, exactly. Current.setNext new node, right? Because it has a setter, so I can update that node. So I set next, that's how I'm going to update it. But what's the value? The value is the pointer to new node, right? New node points to the new node. So set next of current to new node, and voila, I've got it. Yeah.
I have a question. How do you access or return the element of a node?
Right, so you say return, if you have a pointer to the node, if you have a reference to node, you would just say, let's call it node n. You would return n dot get value, right? Because node has two things in it, a value and a pointer. And it has getters and setters for both. Right. All right. And that is how we add something. All right. So, right, okay. Now, we're going to go through the algorithm for remove, and this is the last one we'll go through. Everything else about linked list is some version of add or remove or some variant of something we've seen here. And so hopefully you'll be able to figure it out. There is at least one tricky case that I'll talk about at the end, right? Okay, so let's look at the algorithm for removing from a linked list. So there, again, confirm that index is valid. We've talked about that enough. I'm not going to repeat it. Again, start at the head and keep track with a counter and walk the list until you get to index -1, right? Because we're trying to remove the thing at index. And so we want to stop just before we get to index -1. And what I want to do is I want to essentially take the link of the chain that's just before the one I'm trying to remove and make it skip over and have the one I'm trying to remove and have it point to the one that's past the one I'm trying to remove. That will update my chain so that the one I'm trying to remove is no longer in the chain, right? So we know how to confirm index is valid. That's fine, right? So now I'm going to work with our updated list where we added something already. And so now let's say we want to remove the thing at 2. We just added something at index 2, so essentially we're trying to remove the thing we just added, right? So we're going to walk the chain until we get to not index, but index -1. So if we're removing index 2, we walk the chain until we find index 1, right? So we start at the head, we walk. We don't have to walk too far. Here we are. We've walked the chain until we're at index -1, right? And now the idea is that we want to update the node at index -1 so that it skips over what it used to point to and goes directly to the one after that in order to kind of take that one out of the loop, if you will, to take it out of the chain, right? So we want to repoint the node at index -1. That, in our picture, is the node that currently points to. We want to repoint that node so that it points to the one after the node at index, right? So what is the statement? Right? We can do this with a single statement for setting the next field of the current. Right? We want to set the next field of the current node, this one, so that instead of pointing here, it skips over this and points here instead. All right, so think about what that statement's going to look like, and then we'll get some suggestions. All right, who wants to try this one? Yeah? Yeah. Yeah, right? If I get next, that's just a node, and then I can get next again. So what do you think that statement looks like? Yep. So current.getNext is definitely how we're going to skip over and get it. That will retrieve that. But what do I need to do with that? Yeah, that's right. I'm trying to set the next of current to be that expression that you said, current's next, right? And so it looks like this, right? I'm setting the next field of the current node, and the value I'm setting it to is current's get next. And so that will repoint my next current to now point over here, right? And you'll see my chain now no longer includes that node. What do you think happens to that node? That's all you have to do to remove. What happens to that node that's just sitting out in the heap, right? Yeah, basically. So what happens is Java is known as a garbage collected language. Some languages are garbage collected, some are not. Java is garbage collected. So garbage collected languages mean that you don't ever have to worry about marking some object as being never needed again. So in languages like C or C++ or Rust, those languages make you do all of the memory management. In other words, if some object is never going to be used again, you have to make sure that you tell the operating system this memory is free to use, right? So you have to essentially free memory, right? Java is a garbage collected language. You don't have to do that. What Java will do occasionally is it will go through all of the structures in heap, and it will look for any structures that have no arrows pointing to it. They can have arrows pointing away from it. In other words, I can have this next field inside this, orphan node. It can point to whoever it wants. That's fine, right? That doesn't mean anything. It's all about who points to an object, right? So as long as there's something that points to an object, either something on our local call frame or somewhere in our call frames, our stack of call frames for where they point to heap, or between objects in heap, right? As long as something points to an object, then Java will say, okay, somebody might be using that object, right? There's a way to get to that object through, things that are, available to the program. But if it detects an object that nobody points to, like, for example, our orphan node for inserted item that we just removed, right? Then what Java will do is like, hey, there's no way to get to this object. Nobody refers to it. Nobody points to it. So it's safe for me to collect it as garbage, to throw it away. And so I don't have to do anything with it. I can just fix up my chain just the way I want it, and I don't have to do anything with that extra node. Even if it's there, even if it happens to point there, it doesn't matter, because nobody else can get to that node. It's just an orphan. It's out there in memory. Who cares? Java will eventually come around and garbage collect it. Okay. So miscellaneous notes on implementing linked lists, right? So that is essentially the algorithms in pretty good detail for get, add, and remove, right? So that's most of linked lists, right? So, so right there, that should help you do the homework pretty well. There are a couple of things, like all the other methods are you know, special cases of one of those, or if you just think about it a little bit, are some variants of those, right? We didn't go through index of, for example, but it's just kind of some you know, it's a variant of get, in the sense that you're walking the chain until you find the element, or you get to the end of the chain and you didn't find the element, right? So there are, you know, I didn't give you the whole thing, but hopefully I gave you enough so that you know what you're, you know, what to do, right? There is the one special case you have to worry about when you're adding or removing is if you're adding or removing at index 0, then you also need to update the value of the head field in the linked list itself, because you changed which node is index 0, right? So that's a little bit of a special case that you have to make sure you catch. So be sure that your head node in your linked list is correct, even if you've added or removed at index 0, right? If you're adding or removing something past 0, then you don't ever have to update head, because you're going to walk past it, getting to wherever you need to work with the chain. But if you do happen to fuss with the very beginning of the chain, you got to make sure that the head field inside your linked list is pointing to the first node in the chain, you know, no matter what, right? A couple other things. In order to do index of or last index of, you're going to have to walk the chain, and you're going to be trying to compare the elements in the chain that are stored at the nodes with a specific element that was provided, that, you know, as a parameter in order to the one to find. And so here, in order to compare, like, and remember, we're doing this generically, right? When you write your code, you're going to write it as, you know, linked list of T, where T is some type that will be provided at the time that it gets used. But in your code, wherever you need to refer to the type of an element, it's just whatever T is, right? So how do I compare two elements if I don't know what their type is? Because you'll be like, well, how do I compare? I know how to compare a string to a string. I use the equals method. How do I compare some random object type to some other random object type? I mean, to the some random object type. Two instances of some random object type. It turns out equals will work there also. It turns out every object type has a equals method. All objects of any type have an equals method because of something known as subclassing. Now, we haven't really talked about subclassing, and we're not really going to get into it very much, because that's a 401 topic about object-oriented design, and here we just need to know enough to program in Java, and otherwise we're not really going to get into the weeds about object-oriented design, right? So here's what you need to know about subclassing, right? Subclassing is kind of the same idea as extending an interface, but now it's extending a class. So we talked about how we can define interfaces as, essentially abstract data types, right? And then classes as implementations of interfaces. And we also talked a little bit about how you could define one interface as an extension of another interface and create an is-a relationship, and how that meant that this extended interface promised to have everything the old interface did plus some additional stuff. So the same kind of idea can occur with classes. It's a little different, so it's not exactly the same. But the idea behind subclasses is that you can define one class as an extension of another class. And when you do that, the subclass will inherit all of the fields and methods of the parent class, and then be allowed to provide new fields and new methods that are part of the extension. And just like a sub-interface has an is-a relationship with its parent interface, a subclass will have an is-a relationship with its parent class. And so this, and you can have these, and these can chain, right? I can have a class that, and then a subclass of that, and then a subclass of that, and a subclass of that, and that last subclass has an is-a relationship with all of the classes along that ancestry, that chain of ancestry, right? So it turns out that Java, without really telling you, if you try to define a class that does not have a parent, it will automatically make it a subclass of object with a big O. This is why object with a big O is the universal reference type, because it happens to be the very, very beginning of this subclass chain for any class. Every class is a subclass of object with a big O, which is why every class has an is-a relationship with object with a big O, right? It turns out that the equals method is defined in object with a big O, which is why every object of any type has an equals method, because it's inheriting it from object with the big O. So you can just use the equals method of the element no matter what its type is, and we know it's going to have an equals method because every type has an equals method. And that will return true or false if two elements are equal, right? Now, different classes will kind of use different definitions of equals. So for two string objects, it'll be, are we the same characters in the same sequence and the same length? But for two instances of some other object type, it's going to be something else, right? If a specific type doesn't have a better version of equals, it will simply use the one it inherited from object with a big O, which essentially is the same thing as double equals. It will see whether the two objects are in fact pointing to the exact same object in memory, and then it'll say true if yes, and false otherwise. So not your concern as to exactly how any given type implements equals, just when you're writing the index of and last index of, when you're trying to find a particular element, you need to write that code generically against some random type t. How do you know how to compare some random type t to some other instance of random type t? No problem. Every type has an equals method because it inherited it from object with the big O. So you can just take that element, say dot equals, provide the other element, and then that expression will either be true or false. All right. Any questions about these things? Because that's the last I'm going to talk about in terms of the linked list implementation for doing the homework. OK. All right, so now let's take the discussion away from the practical for how we implement linked lists to the more, the bigger picture. Why? Why do we have these two implementations, right? So, we have these two implementations, one that's array-based, one that is linked list-based, right? But they both do the exact same thing, so what's the point? Why do we need to, right? And it turns out that while we have the interface defined, and that defines our abstract data type, and then we can do axiomatic specification to reason formally about the logic of that abstract data type and its operations, and then we can implement that abstract data type as a specific class that implements that interface, right? The reason we might want to have more than one implementation is different implementations are going to have different performance, both in time and in space, right? That's generally how we consider the performance of a data structure or the performance of an algorithm. How much time it takes to do something, how much memory does it consume, right? Now, the memory requirements for array and linked list are pretty much the same. Now, it's arranged differently, but for the most part, it's the same. Because in an array list, you're going to have an array with memory for all the elements. In the linked list, you're going to have a node structure, one for each element. But in general, it's about the same amount of memory. Basically, you're going to have some amount of memory per element in your list, right? And then a little bit more for keeping track of the size and that kind of thing. But they're pretty comparable in terms of space. But it's time that these two things actually differ in. And when we talk about performance of algorithms or the performance of a data structure, regardless of whether we're talking about time or space, we often use what's known as big O notation. Big O is a way of characterizing the performance of an algorithm or a data structure that captures its fundamental structure but ignores all the constant factors and small little things that aren't really going to matter, right? It's a way for us to describe the time and space performance of an algorithm or a data structure or a operation on a data structure, right? And what we want to do is relate the time or space, and I'll just say time from here on out. We want to relate the time it takes for an operation to the size of the problem, right? In other words, as the size of the data structure grows, as the size of the problem that the algorithm is intended to solve grows, how does that change the time required for a particular operation, or the time required for the algorithm to complete, right? So as an example, let's think of index of, right? So index of as a list operation basically says, I want you to find, if you can, this particular element in the list, returning its index if you find it, right? And the first instance, right? Because this is, list is sequenced. Okay, how does this work for array list? It makes sense. We start at, we look at, we just start at the beginning of the array and go up to size -1, and we just examine each element in the array until we either find the element and then there's the index, or we hit the, we went through all of them and we didn't find it, right? And the same thing for linked lists for the most part. It's about the same thing, right? We start at the beginning of the list, right, at the head, and we walk the chain until we either find the element at one of the nodes, or we end up at the end of the chain where the next node is null, in which case we didn't find it, right? Of course, for the linked list, we have to keep track of our counter so that we can report the index number of the link in the chain. But otherwise, it's about the same in both cases. In both cases, in order to complete the index of operation, we might have to examine every element in the list. And so if we characterize the size of the list that we're working with as of size n, right, then we can characterize this operation as being big O of n, right? So when we say big O of n, that means, or order n, that's another way of saying it, right? Well, or just O of n. When we say an operation is O of n, we're basically saying, well, it's going to take time proportional to n, and n is some kind of idea of size related to what we're talking about. And usually you don't actually have to define n formally because it's kind of obvious from context. In this case, O of n, to say that index of is an O of n operation for a list is basically saying it's going to take me time proportional to the number of items in the list, because n is how long my list is, right? So if n is how long my list is, index of is an order n operation, an O of n operation, right? Now, sometimes there's a difference depending on how you implement, right? So let's say I'm trying to retrieve a particular index, right? In an array list, the first thing I have to do is check the index to make sure it's valid, right? That does not depend on the size of the list. The list could be 2, the list could be 2,000, the list could be 2 million. It doesn't matter how many items are in the list. It takes me exactly the same amount of time to check whether the index is valid, regardless of the size of the list. Why? Because to check if the index is valid, I don't actually have to look at any of the elements. I just have to compare the index I'm looking for to make sure it's not negative and to make sure it is smaller than the size of the list. And the size of the list is available as directly as my size field, right? So the checking the index, that's not an order n operation. That is a constant time operation. When you have a constant time operation, it's going to take the same amount of time no matter what the size of the structure is or the size of the problem is. We say that's order 1. So constant time we talk about as big O of 1. Constant, right? 1, a constant, right? I mean, it's not actually like it's 1 what? 1 millisecond, one instruction, whatever? 1 whatever. It doesn't matter. But the point is, it's a constant amount of time, right? And that's the idea behind big O. We don't really care about the exactly how much, the factors involved. We just want to characterize the operation with respect to some sense of size of the data structure, which in this case we're going to say n is the size of the list. So checking the index, that's an order 1 operation. If it's legal, then we have the array. All we have to do is say, elements, square bracket, index, and square bracket. Done, right? It doesn't matter whether it's a long list or a short list. It doesn't matter if the index is the 0th index or the 8th index or the size -1 index. I can just directly address that element in the array. So even getting the array element from the array is an order 1 operation. So if all the steps in getting a particular value out of a list that's array-based take exactly the same amount of time no matter how long the list is, then that whole operation takes the same amount of time no matter how big the list is. And the getting of any random index in an array-based list is an order 1 operation. That is not true of a linked list. In a linked list, it's going to depend on the length of the list and which index you want, right? If you want the very first index, if you want index 0, that's an order 1 operation because you have the head, and the 0 is the head, and so I can just return back whatever's stored at the head. But if it's anything but head, I'm going to have to walk the list until I get to that index in order to retrieve it. Well, now it's going to depend on the value of index. So if index is 0, it's an order 1 operation. If the index is size -1, it's an order n operation, right? It goes you have to walk the whole list, right? So when the operation might take a different amount of time, kind of depending on which element you're working with, we tend to essentially, what we do is, with big O analysis, is we calculate the average amount of time, right? We say, okay, look, given that I don't know which index you want, sometimes it's 0, sometimes it's n-1, sometimes it's 4, sometimes it's n divided by 2, whatever, right? The best I can do is I can say, well, depending on what index is, right, what's the average amount of time, given all possible values for index, right? So the average amount of time that it's going to take, given all possible values of index, is basically n divided by 2, right? In other words, right, it depends. Sometimes it's quick because it's the beginning of the list. Sometimes it's it's not so quick because it's at the end of the list and you have to walk the whole thing. But on average, you're going to have to walk about half the list, right? On average, a random index is either in the front half or the second half, right? So on average, it's somewhere in the middle. So on average, you're going to walk half the list. We don't care about these factors like divide by 2 or add 1 when we talk about big O analysis. All we care about is what is the function of n, right? And for this case, n divided by 2 is approximately the same thing as n, right? There's an n in there, right? We only care about how it characterizes it with respect to n. Constant time, there is no n because it doesn't matter how big the list is. It's the same amount of time. And that's why we say order 1, no n in there, right? If in the linked list case, when it's going to take about some amount of time proportional to the size of the list, then we say it's order n, right? So that's a big difference between operations there, right? All right. All right, so let's try to fill out this little slide here, right? So we already know that if I want to get the head of the list, that's order 1 for array list and order 1 for linked list because it's the head, and so I can get to it directly. If I want to get to the last element of the list, that's still order 1 for array list, but it's order n for the linked list because I have to go the whole list. I have to walk the whole list before I get there. If I want to get some random I on average, right, then array list, it's still constant time because it doesn't matter which one it is. But on average, our linked list is order n, right? For index of, we already did that one, right? We said it was order n, right? Because we have to go and look for the thing that we're looking for. So that's going to be the same either way, right? Now, how about adding or removing from the beginning of the list? What is the order of operation, or that operation, right, for an array list versus what is it for a linked list? So think about that for a second. I guess we don't have time for active learning anymore. So I'm going to tell you, right? All right. So, well, when you're adding or removing from the beginning of an array list, what is the big piece of work you got to do in order to finish that job? Got to move everything over, right? If you add at 0, you got to move everything in the array over. If you remove 0, you got to move everything down. So to add or remove at the beginning of the list for an array list, that's not a quick operation. That's an order n operation, right? However, adding or removing at the beginning of a linked list, that's super easy, right? You don't have to walk the chain because you're adding or removing at the head. All you have to do is create a node, set up the pointer, update your head to point to your new node, you're done. And it doesn't matter whether the chain is 2 long or 2 million long, it's going to take that same amount of time. Same thing with remove. You simply set head equal to whatever head's next was, and you'll have essentially cut out what used to be head and replaced it with the next thing in the link as the beginning of your chain. And so that will also take a constant amount of time. So adding or removing from the beginning of a list for a linked list is an order 1 operation, right? Now, what about adding removing from the end of a list, right? So adding at size, this should say adding at size, or removing at size minus 1, right? For an array list, this is actually kind of a complicated answer, right? If I have room in my array, if I haven't run out of room, then adding or removing from the end of the list is super easy. It's an order 1 operation, right? If no resize, right? Removing will never resize an array, but the array in an array list, but adding could. But, you know, the end is easy because it's just the next empty array spot if it's available, right? So if I don't have to resize the array, then it's an order 1 operation. Removing is always an order 1 operation for array list because all I'm doing is making size minus minus, right? I'm done, basically, right? You know, I mean, you know, there's no, I don't have to copy anything because it was the end of the list. Whereas for a linked list, I've got to walk the chain all the way down to size minus 1 or size minus 2 as the case may be, or size or size minus 1 as the case may be, and then add there or remove there. So adding or removing the actual creating a node and putting it in the chain, that is a constant thing, but I had to get to the right spot. Right? It was easy when it was the head because I have a special pointer to head that's in my linked list structure, but it's hard if it's the end because I don't have a special pointer for that, so I got to walk all the way down, right? So this is order n to walk the list, right? And then order 1 to do the operation. But since walking the list is part of the operation, essentially, it's order n, right? So it doesn't matter. So if I have an algorithm, if I have something I'm doing where some parts of it are constant time and some parts of it are order n time, you know, it's the whatever is the longest part, whatever characterizes the longest part, that's the thing for the whole operation, right? So even if you have some constant time parts and then an order n part to your algorithm or to what you're doing, the whole operation is dominated by the order n part, right? All right. And then if I'm adding or removing at some random point, then, you know, it's going to be order n on average for array lists because I might have to push things over or copy things down, and order n, right, for the linked list for the same reason. I got to walk to the right spot, right? All of these things, size is empty, clear, right? All of those are super easy to do. Size, I just need to look at my, return size is empty. I just check to see if size is 0. Clear, well, in array list, I just throw away my old array and create a new starter array and reset size. With my linked list, I just throw away my chain and set up head to be null, and, I'm done, right? So all of those operations are order 1 in both implementations. Okay. Okay, so this basically just says what I just filled in, right? Right. So you can improve the performance of adding or removing at the end of a linked list, right? It's essentially, mirroring the idea of our head, right? So our linked list structure keeps track of the head of our list because we have to keep track of the head of our chain in order to then be able to work with the elements that are in that chain, right? There's no reason why you can't also keep track of the very tail of the chain, right? And now you have to make sure that tail gets updated correctly whenever you add or remove at the end of the chain, just like you had to make sure that head gets updated correctly if you add or remove at the beginning of the chain. But we could, by just adding a little bit more space to our data structure, make it so that it's a lot quicker for this specific operation. It won't help in the middle of the chain, but keeping track of the end of the chain as well as the beginning of the chain, keeping track of both the head and the tail, right, as part of our linked list structure, will allow us to add things at the end in order one time, because essentially we don't have to walk the chain. We have a shortcut as an instance field in our linked list structure that says, oh, there's the tail. And so we can just jump straight to the tail, right? And so it turns out we can actually make this better by, we can make that operation better by keeping track of the tail, right? So in general, these are the order operations for array list and linked list in terms of what they do, right? Now, I didn't talk about the resizing case for array lists, right? So that was a little tricky, right? Remember, it was a constant time operation to add or remove as long as you didn't have to resize the list of the array. But if you do have to resize the array, when you add that one new element that's going to resize the array, it's going to be an order n operation because you have to copy the array into a bigger array before you can add the new element, right? So it turns out that if you make sure you double the size of your array, you can essentially amortize the cost of that copying so that amortize across all of your insertions, your order one, right? But it's a little bit of a cheat because it's going to mean that most of your insertions were order one, except every now and then you're going to have an order n insertion when you have to resize the list. And if you analyze like that, if you basically take the cost of that worst case insertion and basically say, oh, I'm going to spread the cost of that. I'm going to pretend that that cost was paid for by a little bit of time for each of the other operations that were really quick. Then on average, amortized across all my insertions, it is order one. But the way to think about this is it's order one most of the time. It's order n sometimes, as a worst case. You only hit that worst case a few times, right? If you keep doubling the size of the list, you're only going to hit that worst case log n times of the list. But the idea here is that operation for array list isn't always order one. It's just order one most of the time, and every now and then it's order n, right? Okay. So why two implementations? Back to our original idea. Why two implementations? Because sometimes, right, we might know about how we're using the list, and some things might be more important to us than other things. In other words, if we can track the head and the tail, assume we have a linked list that knows about both the head and the tail of its chain, then as long as it is the kind of list that the way we're using the list only ever wants to add and remove from either the very beginning or the very end of the list, and we never have to get anything in the middle of the list, then a linked list will always be better, because adding and removing from the beginning and the end is an order one operation, whereas adding or removing from the beginning or the end from the beginning is an order n operation for linked list, and for the end is an order one operation most of the time, but occasionally is order n. So if all you're doing is adding or removing from the beginning or the end of the list, linked list is your friend. If you need to retrieve things from the middle of the list a lot and you don't know where you're going to retrieve them from, then array list is your friend, because getting any random I is an order 1 operation, whereas getting a random I from a linked list is an order n operation. All right, so there are 2 special cases of using a list called stacks and queues. We'll go over that very quickly on Thursday as a beginning. But basically, the nutshell point here is there are 2 very specific uses of list, a stack and a queue, which really do only add or remove from the beginning or the end of a list. And in that case, linked list is always going to be your better implementation. All right, see you on Thursday.